So let's continue with the two-pointer / sliding window playlist from the Strivers A to Z DLC course. But before starting, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is binary subarrays with sum. But before starting off with this problem, please go back and watch my video on count subarray where the sum equals k. Now, this is a problem that I have already done in the arrays and the hashing playlist. Please go back and watch it. So, I'm assuming that you have seen that video. So, let's understand what is the current problem stating. It is stating that you will be given an array. The array will be a binary array. That means it will be containing 1 and zeros in it. And it'll also be given an integer goal. Now, your task is to compute the number of subarrays. Now, what is subarrays? A consecutive portion of an array, right? So you'll have to compute the total number of subarrays where the sum is equivalent to this particular given goal. So let's pick up one of the subarrays. If I pick up this subarray, the sum of the subarray is 1. So this is not equivalent to the goal. So you cannot count it. So which subarrays can I count? Probably I can count this one. So if I take this one, the sum is 2. So I have one subarray, right? Can I take this one? Yes, because the sum is again 2. So the count is 2 now. Can I take this subarray? Yes, I can. So I have 3 subarrays. Can I take this one? Yes, I can. I have 4 subarrays. Do I see anything else? No, I don't see any other subarray. So in total, there are 4 subarrays, and this is what you return. And you might be thinking, hey, Striver, it is the exact same problem because the problem counts subarray where the sum is equivalent to the given k. It is the exact same problem. Now, in this problem, it was given that the array can have positive as well as negative integers. So we did a brute, we did a better, and the most optimal solution was the hashing solution, right? Which was taking a time complexity of bgo of n and a space complexity of bgo of n. Again, I'm assuming that the map is working in bgo of 1. If you assume that the map takes logarithmic of n, you can add that as well. So this was the most optimal solution. Now, this most optimal solution will also work for this particular problem statement. But over here, it is mentioned that it is a binary array. So what we can do is, we can further optimize it. Now, this particular solution was working for positive and negative, but we can still further optimize. The only reason is we're given a special condition that the array contains 1 and zeros in it. Now, if I'm looking to optimize a time complexity of bgo of n and a space complexity of bgo of n, I definitely cannot optimize bgo of n time because I have n elements. I cannot do better than that. That's for sure. So the only place that I can optimize is the space. Can I get rid of the external map that I was using? Again, I'm assuming that you have seen that video. So that is why I'm referencing like that. So I'll have to get rid of that map data structure. So that is where the optimization will come in. Okay, so if I get rid of the map, so I'm looking at a time complexity of bgo of n and a space complexity of bgo of 1. And the problem is involving subarrays. So if I'm not using external data structures, which algorithm comes to your brain? Yes, the 2-pointer and the sliding window. That is where I have to think. But wait, whatever problems I've done till now has been something like finding the longest subarray or a substring. But this is slightly different. Over here, the problem is finding the number of subarrays with a given sum. Number of subarrays, you have to count. You don't have to find the longest, you have to count. So how can I do it? First of all, let's try to analyze how the sliding window and 2-pointer works and see if at all can we solve it by 2-pointer or sliding window. So let's take an example where it is something like 1 00 1 1 0 and the goal is 2. So what do we do generally in 2-pointer? We take a L point, we take a L, we take a R, and we make it stand at the first place. We're looking for a sum of the segment, and we're also looking for the count of subarrays. So let's initially have it as 0. So initially I'm standing at this element. So this is the segment itself. So can I take this number and add it to the sum? I can. Once I've added it to the sum, is it equivalent to the goal? It is not. So what I can do is, I can go ahead and take this R and move forward. At the moment I move it forward, I get a 0. I can add it to the sum. No change. The sum is no more equivalent to the goal. So what I do is I again move the R. Again, the segment will not have it. So I'll again take the R and I'll move it forward. This is the moment I'll add it to the sum, and the sum will be 2. And this is the entire segment. Correct? And the sum is 2, which is equivalent to the goal. So I can say that this is definitely a subarray, right? Can I count this? I can. Once you've counted it, now what is your next step? You'll straight away take this R and you'll move it ahead, isn't it? Right? So I've moved it ahead. I have a 1. So what you can do is, you can add it to your sum, and your sum is 3. Now this is the moment you look for this segment, and the sum is 3, which is not equivalent to the goal. But the sum has exceeded the goal. So thereby, if you keep on adding numbers, to the window, the sum will increase. You'll have to decrease the sum because the sum has exceeded the goal. So if I have to decrease, I'll have to eliminate numbers from the left. I have to shrink the window. If I'm looking to shrink the window, the first element that I'll remove is this 1. So if I remove this 1, what will happen is the sum will again shrink back to 2 and the L will be over here. Now this is where I can say that, hey, is this segment a valid one? It is, because the sum is 2. Can I have a count? I can have a count, so I can count this as well. Now, ideally what I will do is, because the sum is equivalent, I'll take the R and I'll move ahead. If I do this, what happens is, you did consider this segment, right? You did consider this segment, but you could have also considered this segment, right? You could have also considered this segment, but you didn't, because you made sure that the L was standing. Now you might be thinking, okay, keep moving L. Okay, it doesn't work like that. If you keep moving L, what will happen is, you'll miss out on this segment. This is also a valid segment, right? When you move R, and you keep the L here, this is a valid segment, correct? So we are not sure whether to move L or whether to move R. We are in dilemma, right? So I know one thing for sure. As of now, I cannot figure out where to move L and R if I'm looking for a sum equivalent to the goal, because it's saying equal to. And why is the problem coming up? Because we have zeros. On removing zeros, the sum is not getting affected. That is where the problem is coming up. Okay, so we need to find a better solution. So I know that I cannot solve this problem to find out the exact sum equivalent to goal. But can I do this? Let's try to solve a different problem and see if I can figure out a sliding window solution to it. Can I figure out the number of subarrays where the sum is lesser than equal to goal? I know that the problem is asking you to find equal to goal, but I'll try to solve it for lesser than equal to goal. And again, I'll try the same method. Let's take an L. Let's take an R, because we know this is how we deal with windows. We will take sum, we will take sum, and that can be initially 0, and we will take count, and that can also be initially 0. So where am I standing? I'm standing at this segment, so I can add it to the sum. Is that lesser than equal to goal? Is my very simple question to you. Is this lesser than equal to goal? It is. So can I say this segment is a valid segment? I'm like, yes, this is a valid segment. And if it is, increase the count. Perfect. Now what is the next one? I'll take the R and I'll move it here. Now this is where you need to apply some mathematics. I'm asking you a very simple question. When you move it to here, you add it to the sum still stays as 1. And this is lesser than equal to goal. Now if the sum is lesser than equal to goal, even after adding an element, can I say that element individually, can be a subarray where the sum is lesser than equal to goal? I can. So this element individually is a subarray, as well as this element can combine with the left element. So I can say I have two subarrays. I can say two subarrays where the sum is lesser than equal to goal. One is the 0 itself, one is the 1, 0. Agreed? So I add another 2. Okay. What is the next step? I'll move R. The moment I move R, sum will not change. And the sum is still lesser than equal to goal. Why did that happen? Because the element in itself is not allowing it to exceed more than goal. Okay. So can I say this element individually can be a subarray? I'm like, yeah, it can be a subarray. I'm very sure. Okay. Can this be a subarray? It can be. Can this be a subarray? Yes. So what I'm trying to do is, if I'm adding this element, I'm trying to figure out how many subarrays this element can form with the previous valid answer. And that is 1 itself, 2 and 3. That's nothing but the length. So I add 3 more to the answer. Perfect. Let's move R. So this is when I move R, and this reaches 1, and the sum gets updated to 2. Now this time what happened? The sum is still lesser than equal to goal. The sum is still lesser than equal to goal. Okay. So I'm very sure that this element in itself is possible. Okay, if this is possible, how many subarrays can it form? I already have a valid segment. So 1, 2, 3, and a 4. I can form 4, which is typically the length. Okay, perfect. What is the next step? Now this is when you start understanding. I'm going over here. The sum gets increased to 3. Now when the sum gets increased to 3, what happens this time is, I'm saying, hey, on adding this, no. You'll have to shrink. I want under goal. This 3 is exceeding. So I'm like, okay, let's try to make a valid segment. So I'm like, can I just take it off? So if you take it off, the sum decreases and the L will go ahead. And now you stop. Why do you stop? Because this is less than 2, so you stop. Now when you're stopping, now you can definitely say that this entire segment is a valid one. Right? And can I say that this is one subarray, this is another, and this is another? I can. So I again have 4 subarrays. And you might have a question. Hey, wait. Did you consider this? We did. Did you consider this? We did. When we were standing at 0, when the R was at 0, I considered this. If you remember, I considered 0 and then I considered this. When I was standing here, I considered this. I've already considered these subarrays. Perfect. Wow. Next, I'll take R and I'll move it here. So on moving it here, it's still valid. Because the sum is still lesser than equal to goal. So again, you'll add the length, and this will be your overall count. And right after the step, what will happen is R will move out of the boundary and you will be stopping. So now I know one thing for sure. How many subarrays are there that is lesser than equal to goal? I know that. I know an algorithm to find it. Correct? So I'll try to write this algorithm, and after that I'll see how can I find an answer for sum equal to goal, because that is what we'll have to solve. Let's try to write down the algorithm. Can I say, maybe I'll write a function, and the function will be taking a list of integers. Let's call it nums, and it will be taking a goal. Perfect. What is the first step? I need an L, which is 0. I need a R, which is 0. I need a sum, which is 0. Do I need anything else? Yeah, I definitely need a count. Count is 0. What I can do is I can start like while R lesser than equal to something like nums dot size. I can do that. Perfect. Okay, I've done that. what is the next thing that I'll do? The next thing that I'll do is I'll be like sum plus equal to nums of R, I know it. And after this, I'll add it to the answer. Only if I can combine the while and the if check. If the sum by any means exceeds the goal, then you know what to do. You will be taking out from the back, you will be shrinking it, which is nums of L. And you can do L equal to L plus 1. So what I've done is, I have combined a conditional check with a while loop. Because if this is true, it will keep removing. And if it is not true, it will go ahead and add your valid segments. How many valid segments will you get? We did see it was the count. It was the count that was added. And the count is R minus L plus 1. If you remember, we always, if L was here, R was here, we said 1, 2, and 3. That's nothing but the count R minus L plus 1. So I've added this. Once I've added this, you can do R equal to R plus 1 and the while loop can end. Now over here there is an edge case. Please make sure if, or not here, please make sure if the goal is lesser than 0, you can return 0. Again, at the starting I said the goal will be from 0 to n. I'm writing this edge case for a specific reason. You'll understand in the next step. In case your goal is under 0, because the elements in the array are 1 and 0, so you can never achieve any subarray where the goal is lesser than 0. This case will come up when we'll understand. Okay, so I know one thing for sure. I have an algorithm that tells me how many subarrays for a sum lesser than equal to goal. What am I looking for? Sum equal to goal. Can I apply simple mathematics and say, hey, for this, the answer will be, I can call the function with the nums array and I can ask him to find how many are lesser than equal to goal. It will give me, right? And then I can subtract with how many are with goal minus 1, isn't it? That will work. Because if I can get how many are lesser than equal to goal and how many are lesser than equal to goal minus 1, and if I can subtract them, that will be equivalent to goal. That will be, isn't it? And that is why I introduced this condition. Imagine if the goal is given as 0. Whenever you write 0 minus 1, this will be minus 1. And that's when this condition will come into effect. I hope this is clear. This is a very, very simple condition. Very simple maths. Just it. That's it. And that will be the answer. If I have to deduce the time complexity, let's first figure out the time complexity for the function. Over here we have a bgo of n for sure. And then there's a while loop, which is excluding something. Now, overall, it might be running for, like, if you sum it up throughout the course of this while loop, this might run for bgo of n throughout, not at an individual occurrence. So can I say the time complexity of this function is bgo of 2n at the worst possible scenario? And the space complexity is bgo of 1. And this is the worst possible test case. It is not going to happen every now and then. And I'm calling it for 2 times. So can I say bgo of 2 into 2n will be the time complexity and the space complexity will be bgo of 1. So I've optimized my space complexity. Yes, I've compromised a bit on the time, but again, it will be only for extreme bad test cases, not for everything. So this will be the most optimal solution. I'm not discussing the brute better because if you have seen this particular video, you can figure out what is the brute and better. The brute will be generating all the subarrays and the better will be the hashing solution. And this can be the optimal solution. And in case you want the codes, you can find them below. So I hope you've understood it. And that will be it for this one. So if you're still now watching and if you've understood everything, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.